Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Today we will continue our lecture on the topic for chapter 4, active power control or real power control. This is a subtopic of the active power control is the power frequency characteristics of an interconnected system. So the change in power for a given change in the frequency in an interconnected system is known as the stiffness. Okay, so it's called stiffness. Stiffness. So the smaller the change in frequency for a given load change, meaning that the stiffer the system. So normally in terms of the power frequency characteristics, it may be approximated by a straight line, and we call it the K, which is the delta P over delta F, the change in power with respect to the change of a frequency. Okay, so meaning that, so delta P in terms of megawatts and delta F in terms of hertz. That's why your K is normally is a constant, megawatt per hertz, and then depend on the governor and load characteristics. So let's say that we have the delta PG, meaning that the change in the generation with the governors operating free acting, okay, or free governing action. So it resulted from the sudden increase of data load, delta P L. So the resultant outbalance of the power system, because we have the changes, sudden increase in the power load in load. So delta P must be reflected because of the unbalanced systems. So we have the error of the power here. So the delta P is increased, meaning that so the delta P is equals to delta PL minus delta PG. So therefore we can change this value in terms of K. So we mean that delta PL over delta F minus delta PG over delta F, where the delta PL over delta F measures the effect of frequency characteristics to the load, and delta PG is reflect to the PT minus PG. PT is the turbine capacity connected to the network. Okay, and then when the steady state condition again is reached, the load PL is equal to the generated power. So with this one, we assume that we ignore the loss. So we get the K equals to K1 PT minus K2 PL, where K1 and K2 are the power frequency coefficients relevant to the turbines and load respectively. So this is an example, the two interconnected power system connected by the tie line. So this one, and then B is the system with the tie line open. Okay, when sudden change happen, so the tie line is open. So here you have KA, so delta PT, meaning the transfer the power from A to B. You have KB and delta P. Okay, so when the tie line is open, so you have a KA and FA here, and KB and FB here. So let KA and KB the respective power frequency constant of two separate power system A and B as shown in figure. So let the change in the power transfer from A to B, when the change resulting in out of balance power delta P occurs in system B. So the out of balance power occurs in system B. So let's say this one is delta PT, and then delta PT is positive with power transfer from A to B, meaning that because this one positive, meaning that the power is going from A to B. Okay, meaning that from B is negative due to this receiving the power. So we will look at the example for your further understanding. The change in power in frequency in system B due to extra load delta P and extra input of delta PT from A is delta P minus delta PT over KV. So negative sign indicates that a fall in frequency. So the drop in frequency in A due to the extra load delta PT is delta PT over KA. Okay, remember. And then but the change frequency in each system must be equal. So that's why this one in system B, this one in system A, and then you need to rearrange the equations. At the end of the day, you get your delta PT is equal to plus KA plus KB delta P. So this is common equations. And next, let's say we consider the two systems operating at a common frequency F. When A is exporting power, delta P to B. So the connecting link is now open. This one is the case B. Okay, now the link is open and A is relieved from delta PT, and assume that frequency FA and B has delta PT is small load and assumes FB. So this one is in terms of frequency in A, this one is frequency in B. So your FA equals to F plus delta PT plus KA, and FB equals to F minus, because you have a frequency, it's drop in frequency, delta PT over KB. So this one also, when you do the rearrange these equations, okay, meaning because this is F, so you can do the rearrangement. Okay, so F equals to FA minus delta PT over KA. So this one, F equals to FB plus delta PT over KB. So this one is F, this one is F. You can make it similar. So FA minus delta PT over KA equals to FB plus delta PT divided by KB. Okay, so you need to rearrange these things. So FA and FB you can bring to here. So FA minus FB equals to delta PT over KB plus delta PT over KA. So this one is common, right? So basically you can rearrange which one. So you rearrange that things, you get what? FA minus FB equals to delta PT, this one is KB KA, and then this one is KA plus KB. Okay, so you rearrange, you bring that one is up there, so you get KA KB divided by KA plus KB equals to delta PT over FA minus FB. So you get these equations. Okay, hence by applying the link and measuring the resultant change in FA and FB, the value of KA KB can be obtained. So this is the coefficient of the stiffness of the KA and KB. So in practice, when large interconnected systems are linked electrically to others by means of tie lines, the power transfer between them are usually decided by mutual agreement, and the power is controlled by regulators or AGC. So as the capacity of the tie line is small compared to other systems, care must be taken to avoid excessive transfer of power and corresponding cascade speed. So in order to make sure that you all understand, let's take a look at the example. Okay, so we have two systems, system A and system B. The system is 50 Hz, the frequency is 50 Hz power system connected by tie line, which carry 1000 megawatts from A to B. So as shown in this figure. After an outage of the system or the line shown in the figure, the frequency in A increased to 50.5, while system B decreased to 49. So calculate the stiffness of each system. Okay, so what is the stiffness? Stiffness is KA and KB. So to answer the question 1, so when the change occurred, so delta PA equals to 1000, right? Because it's 1000 megawatts transfer from A to B, and delta PB is minus 1000 megawatts because this one is going out, so it's positive. It's receiving is negative. So we use the equation, this one, FA plus, because it's system is a similar from this example. So your FA equals to FA plus your change delta P is 1000 divided by KA. This one is not FA equals to F plus 1000 over KA, and then your FB equals to F minus 1000 over KB. Okay, so now we have our FA. So we write again, FA equals to F plus 1000 divided by KA. FB equals to F minus 1000 minus over KB. So your F frequency is 50. When the tile is open, your frequency A is become 50.5 Hertz. This one is 1000 over KA. So you solve these things, you can get your stiffness of KA is 2000 megawatts per Hertz. So this one similar. This one is 49. 50 minus 1000 over KB, and then you solve these things, you can get your K is 1000 megawatts over Hertz. So that is the solution for number 1. Okay. 2. If the system operate interconnected with 1000 being transferred from A to B, calculate the flow in the line after outage of 600 megawatt generator in system B. So now when the change of flow is in line is theta P. So let's say if change of flow in line, we call it delta P. So for system A, it is negative delta P over KA, so equal to negative delta F, right? And for system B, because you have 600 outage, okay, calculate the flow in the line after outage of 600 megawatt generators in system B. So in system B, it is 6 minus plus delta P over KB. This is equals to delta F. Okay, so delta F is similar. You can make it the equation similar. So delta P minus delta P over KA equals to minus 600 plus delta P over KB. Okay, we already know our KA and KB. Negative delta P over 2000 minus 600 plus delta P divided by 1000. So you solve these things, you can get your delta P equals to 400 megawatts. So the flow in the line basically is 1000 plus 400 megawatt after the line outage, so meaning that it is 1400 megawatts. Okay, I think that's all for this example and this topic. So anything we will discuss during our online class later. I think that's all for today. Thank you very much.